you have to estimate a lot. Try to figure out what the central code parts are, routines and classes, and modules in general, and whether there are isolated code regions, which is an excellent candidate for that code. And this information about central code parts and candidates for that code can be derived from relationship graphs, inclusion graphs, that's binary object import, like PE import, or include use and include and Java import and class usage. That's nasty actually. I thought I could just go ahead and read all the import statements in the Java file and then I'm done, but it's a bit trickier. There's a whole host of other relationship graphs, and I haven't implemented all of them. I did inclusion graphs. I didn't do any of these up to now. I'll stop that. Control flow graphs, I did inheritance graphs up to now, no, but it's readily available in Java.doc, I believe. You get these pretty inheritance graphs if you turn on some option or other. Membership graphs are also interesting, but I don't believe that Java.doc or Doc6 do that right now. Function call graphs, haven't done that because of lack of time. Data flow graphs are a bit trickier if you work with source code, especially if you work with C source code. Control dependency graph and data dependency graphs are the same issue as data flow graphs, plus they're rather esoteric. I should probably explain a bit of what all these graphs are about. Inheritance graph, it's clear, so if you have a class hierarchy and one class inherits from the other, so that's clear. Membership graphs, if you don't extend code by inheriting, but by just including an instance of the class in question. Function call graphs should be obvious. So the nodes are functions, and two nodes have an edge if one function calls the other. Control flow graphs are usually done as basic block graphs. So you have alternate decisions, if then else, and split up. We're going to see them later, so I don't have to elaborate here. Data flow graphs, just are also based on basic block graphs, and then you just follow a certain variable or a certain value through the basic block graph and see how it gets manipulated and where it gets manipulated. Control dependency graphs and data dependency graphs are too esoteric to elaborate on right now. If somebody is interested in compiler design anyway, read Steve Mochnik, Advanced Compiler Design and Implementation. It's explained beautifully there. So, I don't know, graph theory background? Not really. Component is a really simple concept from graph theory. You have a heap of nodes in some place and a heap of nodes on the other, and one heap is connected among one another, but they're not connected, interconnected. So you have two separate heaps of nodes, and the two separate heaps of nodes are called components. And if you find in the name graphs, inclusion graphs, or control flow graphs, or call graphs, more than one component, this may hint that there's dead or unused code in this code, but it need not necessarily be, especially in C, where you have all sorts of funky function pointers, which are not easily captured when you generate these graphs. So, if you want to know how complex code is, the obvious measure is lines of code. That's not really very useful if you want to use it as an absolute measure. So, how complex is a file with 100,000 lines of code. That's not a very useful statement, but if you have a number of files and compare them and say, okay, there's one file which only has 10 lines of code, I probably don't have to put much time in there, and there's probably not much interesting functionality in there. Then you have the infamous relationship graphs, which I mentioned earlier, inclusion graphs, control flow graphs. From their structure and complexity, you can usually always also say something about the code complexity. If it's very intricate graphs, then you have high code complexity, which is not necessarily saying that the code is very complicated or that the functionality is very complicated to achieve, but it says that possibly the developer has smoked a bit too much and didn't do proper software engineering, which makes it harder for you to audit the code. Because the more structure there is in the code, the easier it gets to find your way around it. Estimating code quality. Comments are somewhat useful in that, but not. There's not a linear relation between amount of comments and code quality. So there can be tons of comments in code saying nothing. That's the paper line approach. If somebody is paid by the lines that they write, they tend to draw fancy function headers, repeating all the arguments and drawing fancy ASCII art around it. So that shows up as lots of comments, but it's not really useful. So what you look at is the frequency and distribution and extensiveness and type, and you can usually just see certain patterns. So if you, I have a picture after that, I'm going to show you them. Then there's distribution of certain keywords in a file, typical candidates, bug, to-do, fix me. And if you graph this really quickly, the blue stuff is comments, the gray stuff is code, the red stuff are occurrences of bug, fix me, hack, to-do. This is not such a good piece of code, it's very short, but has a lot of these occurrences of fix me and hack. And in here, one pixels, one line of source code. And the squares are separate functions. And a very typical pattern in this paper line code is that you have one function, so one gray box, and then above it a huge blue box, and it repeats over and over. And if they're rather uniform, the blue boxes, that's a good indicator that the comment is going to be useless because the programmer just wants to spend time writing comments. So that's one instance where you have one picture and can see almost immediately, give an estimation of what the code is going to be like, or identify typical instance of strange code. Because usually, I don't know if you follow me there, but usually if someone spends their time painting fancy function headers, comments, I don't have much confidence in their coding skills immediately. Another interesting topic is code history. Code history can be very revealing. It's another instance where you have one picture and can immediately give an estimate of how good the code is going to be. And it's also nice that data on code history is in a lot of projects readily accessible, so via CBS or Subversion or Rational is more often used in commercial settings. And there's a nice heuristic measure for code quality there, because all code, few changes is usually bad. It means it was written long ago and somebody forgot about it and never cared about it anymore. And it was probably not really heavily used, so that's probably a part of the code that wasn't often reached. But that's not to say that it's never going to be reached. So if you can find old code with few changes and then make the software enter these code parts, you're likely to find interesting bugs. older new code that has seen massive changes is also not necessarily bad, but very suspicious, because with massive changes usually also come lots of bugs. If you see old code with many incremental changes over time, that's good. That means that it has been maintained continually and it has been in use and people have found bugs in it and removed bugs from it. And in new code, there's not really much you can say. But it's also just an estimate, but it's so nice because you can see it at a glance. So I haven't actually implemented that feature, that's just a mock-up. A is old code, so the funky bubbles there are the code changes, and this is timeline, and each string is one piece of code. So the code in A is rather old and has seen quite a few incremental changes over time, so that's less likely to be riddled with holes. Code B is compared to that relatively new and has seen a lot of massive changes. Code C is very old, but somebody obviously forgot about here. And D is very new, you can say much about it. And if I had to choose, if somebody said, okay, you have time to audit exactly one of these pieces of code, I'd go for either C or B, because that's most likely to contain bugs. A pointy view, while I was preparing this talk, I also noticed that there's a revision history view available from FreshMe, 2 years old. I couldn't get it to run, it just crashed on me repeatedly, and I didn't really have the nerve to figure out why. It's an Eclipse plugin. It sort of, well, stay with me. Sort of does what I was talking about. Grabs the code pieces over time and changes as little bits. So if it runs, it's probably cool. Experiment 1, spatial metaphors for code. This is all highly experimental. I don't have any user interface lab behind me to back this up. This is all just speculations from my daily practice experience when auditing code. Okay, code is complex. Unless you have Hello World, which is not very interesting. Not that you can introduce bugs in Hello World, but usually it's not Hello World you get to look at. So you have lots and lots of complex abstract structures. Introducing a spatial metaverse for source code might help you to free up some cognitive resources and make relations among the different core parts apparent, and provide a sense of orientation. When I'm faced with a repository of new code, there's always this sense of being completely lost. I have no idea where I am, I have no idea where to start. And this only gets better after a week or so, but relies heavily on my explicitly building in my head representations of this code. And I was thinking about whether you could make this explicit. So the basic idea is to convert abstract properties of source code into spatial properties. And suitable features are obviously size and relationships between core parts, and occurrences of features like search terms and references to code entities. And you can choose whether you want to treat the representations as general graphs, so more if you come from a more graph theoretical background, or just as maps, so you draw maps and try to chart your ways around in code maps. Most basic thing is to graph the directory hierarchy inside.